Section 5.3, at least the first half of it, I guess, or roughly the first half of it, deals with rational equations. And the way that you would solve a rational equation, at least we have a reference point for, because it's not too different from the way that you would solve an equation that had fractions in it, that wasn't rational. So like a polynomial equation with fractions in it. And there, what you would do probably to simplify things would be to clear fractions. That's also what you do here, right? I mean, when you look at rational expressions, they look like fractions. It's one thing divided by another thing. But you have to watch out for possible restrictions because there might be numbers that would result in dividing by 0. Those can't be answers. So what you have to do somewhere in the problem, either like right at the beginning, like I've got it right here, or maybe at the very end, just to kind of double check, is to see if any of the solutions that you get when you solve the rational equation result in a denominator being 0, because if that happens, you got to throw those solutions out. They're extraneous. So let's see how this works. With this first example, it's just one rational expression set equal to another. So you could cross multiply, which is what I do down here. But first, I just check the restrictions. So to get that x plus 1 in the denominator to be 0, which would cause some trouble, that's going to happen if x is negative 1. All right, so that's how I got this restriction here. And then for the one on the right side, for x minus 1 to be 0, that's going to happen when x equals 1. So those are restrictions. So our solutions can't be 1, can't be negative 1. Just have to kind of keep that in the back of your mind for the rest of this, I guess. So I did cross multiplying here, which is kind of the shortcut. Really, if you're going to clear fractions, you would multiply both sides by x plus 1 times x minus 1. But the effect of doing that is identical to the effect of cross multiplying. So cross multiplying is a little bit shorter, so I did that here. You end up with one polynomial equal to another polynomial. I put everything on one side, and then the left side is going to factor. So you get either that x is negative 3 or x equals 2. And then you just have to check these against the restrictions. Okay, well, these look okay, right? Neither of these numbers are 1 or negative 1, so we're okay. So no extraneous solutions. So negative 3 and 2 are both going to solve the equation. All right. Well, how about another one where the denominators are maybe a little bit more complicated? So here, the denominators are x squared minus 2x and x squared minus x. You could turn this into a cross-multiplying situation, which is what I would do. You don't have to if you wanted to clear fractions just the way it is right now. I guess if you factor those denominators, the one on the left would be x times x minus 2, and the one on the right is x times x minus 1. So you could just multiply both sides of the equation as it is right there by x times x minus 2 times x minus 1, and that would work. But I think this is easier, so I did it the other way. I did check the restrictions, though, first. So in order to get that first denominator to be 0, either that would happen if x was 0 or if x was 2. Since x squared minus 2x is going to factor into x times x minus 2, right? So those are going to be the two possibilities that would give you a 0. And then the other denominator, x squared minus x, you can factor an x out of that. So x also can't be 1, right? You get this duplicate here that x can't be 0. We already know that, so having that duplicate doesn't really affect anything. But then if you cross multiply, you end up here. Once again, I just put everything all on one side, and it does factor. So either x is 0 or x is 4, but x can't be 0. Because up here, 0 is one of our restrictions, because it'll actually result in both of these denominators being 0. Just one of them being 0 is enough, but that'll actually result in both. So we can't have x be 0, so that's extraneous, but 4 is okay. Right, 4 is not a restriction up here, so 4 is fine. So here, that's going to be the only solution. Example 3 on the next page, I guess this is one where you couldn't cross multiply. It's not clear how you would do it with 3 terms, right? You got to have 2 terms for that. But we can just clear fractions by multiplying by the least common multiple of the denominators that are there. That'll be fine. So first thing, check for the restrictions. X being equal to 3 would make that denominator 0. X being equal to 0 would make that one 0. So those are our true restrictions. X can't be 3, X can't be 0. All right, then clearing fractions. If we multiply both sides by x times x minus 3, so the least common multiple of the two denominators, then here I did it. So when you multiply 2x over x minus 3 times x minus 3, the x minus 3's are going to cancel. So I already canceled them here. Then the second term, I already canceled the x's, right? You'd have 4 over x times x times x minus 3, and the two x's are going to cancel out. And then minus 6 times x minus 3. And then the other side, 0 times whatever is still just going to be 0. On the left, I guess there are things to multiply out, right? Distribute the 4 to get the 4x minus 12. Distribute the minus 6x to get the minus 6x squared plus 18x. Combine terms, you end up here. And then I divided both sides by -2 just to make the numbers a little bit easier to deal with and a little bit smaller. And then from here, this doesn't factor, so I use the quadratic formula. And what you end up with is 11 plus or minus radical 73 over 4. Both of those numbers are going to be fine, right? The restrictions are 3 and 0. These numbers are not 3 and they're not 0, so we've got no extraneous solutions, so we're good to go with those two. The fourth example, the other one on this page, denominator of x plus 3, denominator of x plus 5, and that is x plus 3 times x plus 5. So the least common multiple of the three denominators is actually the one that's on the right. Okay, well this is another one where you couldn't use cross multiplying because we've got 3 terms instead of 2, but we know what the least common multiple of the denominators is, so we're going to multiply both sides by that, and you can see it down here. First, I did write out what the restrictions are going to be. -3 is going to cause trouble here and here because this one on the right factors into x plus 3 times x plus 5, and then -5 is going to cause trouble here and here. So those are our two restrictions. Can't have x being -3, can't have x being -5. Both of those result in dividing by 0 somewhere. All right, then to clear fractions, you multiply both sides by x plus 3 times x plus 5. And then here, in this first part, I already canceled out the x plus 3s. Here, I already canceled out the x plus 5s. And here, if you multiply 2x over x plus 3 times x plus 5 by x plus 3 times x plus 5, you get a bunch of cancellation and you're just left with 2x. All right, well then, I guess distributing a 4 is about all you got to do to get here. Combining terms, and you can solve for x. Right, it's not too bad. End up with that x has to be -17 over 3, and it looks like that's okay because it's not either of these restrictions up here. So yeah, no extraneous solution. So the only solution that we're ending up with is -17 over 3. Compared to solving a rational equation, solving a rational inequality is a little bit different. So what you want to do, or I guess first what you don't want to do. Clearing fractions initially, like right off the bat, is a bad idea. It actually makes the problem a lot more complicated. Or with something like this where it looks like you could cross multiply, that's also a bad idea and it'll make things more complicated. What you want to do is put everything on one side of the inequality. It doesn't matter which side. Just get everything on one side with a 0 on the other. Then from there, the side that doesn't have a 0 on it, you want to turn that into one single rational expression, which would involve getting a common denominator and then combining the numerators together. And then from there, you can basically check intervals of values. Because then the only place where you might end up with a sign change, so like where the expression might go from positive to negative or negative to positive, would be either at a 0 of the function, which would be a 0 of the numerator, or at values where the function's undefined, where you get an asymptote, because there you could have negative values on one side of the asymptote and positive values on the other, or vice versa. So where do you get asymptotes? Where the denominator would be equal to 0. So basically, once you have that single rational expression on one side, you just have to figure out where the numerator is 0, where the denominator is 0. You use those values to break up the number line, and then it's a few test values, and you'll get it from there. Okay, so with this one, get everything on one side, right? I said that was the first thing. So that's what I did first. I subtracted 3 over x plus 1 from both sides, and you end up here, right? We've got the 0 over here. We've got everything else over here. But then this thing on the left, the 5 over x minus 3 over x plus 1, you want that to be one expression. So you need to get a common denominator, and that way you can combine the numerators together. The easiest common denominator here would just be the product of x minus 3 and x plus 1, so that's what we're going to do. So I multiplied 5 over x minus 3 by x plus 1 over x plus 1, and then multiplied 3 over x plus 1 by x minus 3 over x minus 3. And then that'll do it. We'll get the common denominator of x minus 3 times x plus 1, and then the numerator will be 5 times x plus 1 minus 3 times x minus 3. You can see those pieces right up there. then we can distribute the 5 and the 3 and combine terms together, and we end up here. So, okay, let's see where the numerator is 0. Let's see where the denominator is 0. So where's the numerator 0? Well, that's when 2x plus 14 is 0, so ultimately that's when x is negative 7. And for the denominator, those kind of jump out. It's going to be when x is 3 and when x is negative 1, right? So if we use the negative 7, the 3, and the negative 1 to break up the number line, so putting them in order, left to right, you have negative 7, then negative 1, then 3, then we just have to check these intervals. So 4 intervals, you need a value for each one. So the one on the far left, I picked negative 8. So I didn't even worry about the values because we're not going to graph anything, right? There you need the actual numbers, right? Absolutely. But here we just need to know, is it positive or negative? So what I did here, just to kind of shorten things up and to be able to fit it on this page, to be perfectly honest, was that I said, okay, for this part, the x plus 7, negative 8 goes there, then negative 8 minus 3, and then negative 8 plus 1. Then I said, all right, that's a negative number. So, right, it's negative 1. So negative times a positive, that's a negative. Down here, that's a negative, and that's a negative. Negative times negative is positive, and ultimately that's a negative over a positive, which is negative. So negative for that interval. And then I did the same thing for this one. Like for negative 2, I said, okay, this is a positive, so it's positive times a positive, so you get a positive on top. And then on the bottom, that's negative, negative times a negative is a positive, and ultimately positive over positive is positive, right? Put a 0 in there. All right, well, positive on top, right? It's a positive times a positive again. On the bottom, that's negative and that's positive. So negative times a positive is a negative. You divide here, you get a negative. Then down here, they're all going to be positives when you're all the way over on the right side. So positive, positive, positive. Everything's positive here. You're going to end up with a positive when you do all the simplification. So that's really all that you have to do. You don't have to get the actual numbers. You can if you want to, but as long as you get the sign correct, I think that's enough. And then what we're looking for is where the expression is positive. So here, there's a plus. Here's a plus. So I go back up to the interval between negative 7 and negative 1. We want that. And then 3, or I guess really above 3, right? It's a strict inequality. So, well, and 3 is a restriction on the denominator. It's not a 0 in the numerator anyway. So just everything above 3 and then between negative 7 and negative 1. So there's the solution from negative 7 to negative 1, that open interval, and then the open interval from 3 to positive infinity. Example number 6 actually looks easier than example number 5 because there's a 0 already on one side of the inequality. So that's nice. We don't have to get a common denominator or anything. We're all set. So we can jump right to seeing where's the numerator 0, where's the denominator 0, and splitting up the number line. So the numerator is 0 when x is negative 1, denominator is 0 when x is 4. This might be one where you can just kind of eyeball this thing to figure that out. But we go over here, we got 3 intervals now, and we split up the number line using the negative 1 and the 4. So we got to check each interval. So negative 2 is for my interval on the left. So if I substitute in, that's a negative on top, negative on the bottom. The negative divided by another negative is a positive. So positive up there. In the middle, we got a 0. That ends up being positive on top, negative on the bottom. So positive over negative is a negative. And then for bigger than 4, 5. And then that's a positive over here. So that's a positive. All right. Well, then we want the part in the middle because if you look up here, we want where it's less than or equal to 0. So we want that. And the other thing, which I kind of got right and I kind of got wrong, I realize that now when I'm making the video. I wish I'd caught this earlier. You need a bracket around the negative 1. You should actually have a parenthesis around the 4 because the 4 is coming from the denominator, so it's actually a restriction. So that bracket here around the 4 is actually wrong. This should be a parenthesis. But the reason that you need the bracket around the negative 1 is because this is a less than or equal to. So when you get 0, which happens when x is negative 1, you need to include that. So that bracket is right, but that really should be a parenthesis right there. Sorry about that. Then going to the next one, number 7. All right, so we have something new this time, which is that there's a squared term on top. So this is another one where it's already set up for us. We got the 0 on one side of the inequality. And we just have to figure out, okay, well, where is the top going to be 0? Where's the bottom going to be 0? What x values are going to result in that? We can break up the number line that way, and we can go from there and get some test values. All right, so How could the top be 0? Well, for x plus 5 squared to be 0, x plus 5's got to be 0, so x needs to be negative 5. For the bottom, x squared minus 4, for that to be 0, x could be 2 or negative 2, right? Because for x squared minus 4 to be 0, that's when x squared is 4. So using the square root property, x could be plus or minus 2. All right, so then when you break up the number line, you need negative 5, negative 2, and 2. And then you just have to check those 4 intervals. So you go through and check them. You're always going to get a positive on top because of that square, right? Look, every single time, plus, 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 you can barely see it there, but that's plus 2. So the only thing you really have to check is the bottom. So like here it's a positive because that's 36 minus 4, right? So positive over positive, overall it's a positive. Here that's a positive, it's 5, right? 9 minus 4. All right, you get a positive there. Here it's negative, right? You're going to get negative 4, so positive over negative, you get negative altogether. And then for the last one, I picked 3 for a number bigger than 2. All right, well, that's another 5, just like negative 3 was, so that's a positive there. All right, so it goes plus, plus, minus, plus. We want the plus parts, so that part, and that part. And here I did it right with the brackets because I've got it around the negative 5 because of the non-strict inequality here. But then you don't want to include the negative 2 or the 2 because those are denominator restrictions. So it would be this, but then the union of those first 2 intervals, there's no gap between these. Not with the negative 5 being included. So you can combine these into one thing, which I did down here, just to write a little more efficiently. So it would be the open interval from negative infinity to negative 2 union with the open interval from 2 to infinity. All right, one other thing to notice here. If I go back up here, signs are alternating. Even if I go back to the last page, the signs are alternating up here. If I go down to example number 7 that we just did, they don't alternate around the negative 5. How come? Because x minus 5 is squared. So it's just like with polynomials. If you have, like with a polynomial, if you had a factor that was squared, then the sign wouldn't change, right? That was where it would just touch the axis and then stay on the same side. It's a similar sort of effect that if you have roots or restrictions of odd multiplicity, you're going to get a sign change. Even multiplicity, you don't. So that actually works the same way that it did with polynomials. So even though it's a little bit different, right? You have like restrictions and things that you don't have with polynomials, but that concept still works. The next couple of examples I tried to set up like ones in the homework because they tend to do this where it's this 3-part question where you've got the equation and then the 2 strict inequalities. So the equation, that's one where you could cross multiply, right? Where here the cross multiplying is not too bad, right? You're going to get x plus 6 equal to 1 times x plus 2. But that has no solution because for that to be solvable, you would have to have 6 equal to 2, and that doesn't work. Okay? Well, then what about the other ones? B and C, I would argue that you could do them at the same time and also that you should do them at the same time. Because the solving is identical, and the only thing that would change is in B, you're looking for where you get negative values, and in C, you're looking for where you get positive values. If you just do the number line, you would get all of that at once. So you might as well just do B and C together. That's what I think. So with B, and I have it set up to where it's solved for B, but the solving for C would be the same, just the inequality facing the opposite direction. So you want to get the 0 on one side, so I subtracted 1 from both sides. You want to get a common denominator, so 1 multiplied by x plus 2 over x plus 2 will get you here. And then you can combine the numerators together, and that's just going to be a 4, ultimately. Right? So 4 over x plus 2 is less than 0. So when you look at this thing, you go, oh, well, the only value that would make either the numerator or denominator 0 is negative 2. That's going to make the denominator 0. Right? Nothing's going to make that numerator 0. So you go up here, we just have to check to the left and the right of negative 2. So I put in negative 3 for the left side, and you end up with negative 4. You go, all right, that's negative over there. Over here, I figured the easiest number to pick would be 0. You get 4 over 2, which is 2. All right, positive over there. So for B, the solution where you would get negative values of 4 over x plus 2, which would be the equivalent of having x plus 6 over x plus 2 less than 1, it's to the left of negative 2. So open interval from negative infinity to negative 2. And then for part C, It's the same simplification as part B, you just end up with the inequality facing in the opposite direction. So you're just looking for where 4 over x plus 2 is positive. We already know that because it's right here. It's when x is bigger than negative 2. So the solution to part C, it's the open interval from negative 2 to infinity. There's not really extra work to do there, and I don't view this as a shortcut at all. It's the work is absolutely identical, so basically you do B and C simultaneously. Example number 9 is the same kind of situation where we've got equation and then the two strict inequalities. The equation, well, we can't have x being negative 2 because that'll make the denominator 0. But then other than that, for this expression to be 0, you need a 0 on top. And I said, all right, fine. We'll set x squared minus 3x equals 0. That factors as x times x minus 3. So for that to be 0, either x would have to be 0 or x would have to be 3. So those are the two answers to part A. Because neither of these are restrictions, they're both going to work. All right. Part B, parts B and C, I guess, together, right? We're going to do what we did last time. But we've already got a 0 on one side. So then you just have to see where's the numerator 0, where's the denominator 0. We already know where the numerator is 0, we just solved that. And then where's the denominator 0? Well, we knew that too, because that's our restriction. So we have to use negative 2, 0, and 3 to break up the number line. And then we've got to have test values for those intervals. So for negative 3, and this is easier when it's factored, so I use that factored version right there. So the negative 3 times negative 6 over negative 1. So negative times negative, which is a positive on top, negative on the bottom, you divide, that's a negative. Then for negative 1, for between negative 2 and 0, I did the same thing. That's a negative times negative on the top again. So that's a positive. Now there's a positive on the bottom. Positive over positive is positive. For 1, you end up with a positive times a negative on top. So you get a negative on top divided by a positive, and that's going to be negative. And then for 4, so for something bigger than 3, positive, positive, positive. When everything's positive, you're going to simplify down to a positive. And for B, we're looking for where it's less than 0. So that's out here below negative 2 and then between 0 and 3. And then for part C, it's going to be where the pluses are, right? So we go down here. That's where one of the negatives was. So negative infinity to negative 2. And then the other one was from 0 to 3. And strict inequality, so open intervals everywhere, right? And strict inequality here too. So these are where the pluses were. So negative 2 to 0, there was a plus between those, right? You can see it right here because of the negative 1. And then from 3 to infinity, right, that's the 4, giving us that plus. So it's those two intervals where you would get the irrational expression to be positive.